Welcome back, class. In this video, I want to talk about how we look at the strength of an acid and or base. So previously, in general chemistry, we talked about the idea of electrolytes, right? And we had strong electrolytes and weak electrolytes, and these were based on the idea of the amount of ions in solution. So the more ions in solution, the stronger the electrolyte would be. So, for example, if I dissolve sodium chloride in water, right, it undergoes full dissociation, forms lots of ions, right? We consider that a strong electrolyte. And remember, the term electrolyte comes from the ability to conduct electricity, and that's possible because of all the ions in solution. So we sort of pull this idea into acid-base strength because, of course, if we think about the definitions that we just talked about, acids and bases are producing ions in solution, right? Hydrogen ions from an acid along with the other negative ion, and hydroxide ions from a base along with the other positive ions. So we can think about strong acids versus weak acids in the same way in terms of how much of the acid molecule or base molecule gets converted into the ion form, right? Or undergoes, in Bronsted-Lowry notation, right, undergoes the proton transfer. So if we call something a strong acid, which is also a strong electrolyte, it basically means that all of the acid molecules have ionized and turned into their ion form. We've made, all of our acid has gone to produce hydronium ion. A strong base, same idea. All of the molecules of base have gone on to produce hydroxide ions, either through simple dissociation if we have an ionic base like sodium hydroxide, or perhaps through a reaction with water, right, to generate the hydroxide ions. Now, if we call something a weak acid or base, it simply means that only a small percentage of the molecules get converted into the ion. And so a weak acid, right, only a small percentage of the acid molecules ionize in the water. And a weak base, only a small percentage of the base molecules form hydroxide via dissociation or reaction. And something to sort of understand right away is that there is a big gap here, right? And when we say strong, essentially we mean 100%. When we say weak, we mean a tiny percent, right? So, just to give it, it's going to be, less than 10%, right, is going to be probably a reasonable ionization percentage, right? It's going to be a small percentage, maybe, down to, a percent or two. So you're not going to see acids and bases that are 60% ionized, right? It's either everything or some small percentage. Okay, so let's look at these just a little bit more in detail. First, we'll look at acids. And again, strong acids, we basically say they are unidirectional, right? That all of the molecules exist as the ion form. So if we think about the Bronsted-Lowry definition and our conjugates, right, we'd say that everything of our original acid has been converted into its conjugate base, right? And so the equilibrium, right, lies far onto the product side, to the extent that we typically refer to it as just a unidirectional reaction, right? We don't even usually think about it as an equilibrium. And in this particular scenario, right, the hydronium ion concentration in solution is going to be equal to the original concentration of the acid that we used, right? So if we want to know the concentration of hydronium, all we need to do is know what the concentration of acid that we started with, because there's 100% conversion. A weak acid, right, more complicated, right? Because now only a small percentage of the acid molecules form hydrogen ions or hydronium ions, right? And again, it's being generous when I've less than 10, a lot of times, again, like I said, it's a very small percentage. It's less than 1% for some. Now, so what this means is the hydronium ion concentration is much less than the original acid concentration. So identifying the hydronium ion concentration in these weak acid systems or equilibrium systems, right? So these are going to be, we're going to look at these as equilibrium systems, and they're going to be reactant favored equilibrium, right? Because most of the molecules remain on the reactant side, right? It only goes a small extent toward product side, right? Formation of the hydrogen or hydronium ions, right? To the conjugate side of the reaction. And we'll see that when we explore the equilibrium constant for these types of reactions. So if we look at these more pictorial, right, we have the classic HCl, where essentially we have only ions present at the end. And again, we often will just simply refer to this as a unidirectional reaction, not as a reversible or equilibrium system. Whereas a weak acid, we can see that we get just a small amount of ions, but most of it still exist in the acid form, right? Only a small amount has gone on to form the ion form. And so we have a more of a true equilibrium where we have some of each, but again, these are going to tend to be very reactant favored equilibriums. So just to give you a couple examples, now note in these pictures, in these tables in the book, they always have the acidic, or at least where the acidic hydrogens are, highlighted in red. So if there's a reason you need to tell the difference. So some strong acids. Now, I always get the question about how do you know whether you have a strong acid or weak acid, if you're just given a material. Well, there's no way to functionally just look at something and tell. But what we can do is remember the 6 strong acids, because that's all there is. So the acids that are drawn in this table, these are our strong acids. So we have 3 binary acids, right? What we call the halo acids. So HCl, HBr, HI, all of them except for HF, which is a weak acid, as we saw in the previous slide. We have 3 oxyacids. 2 that we've talked about, nitric acid and sulfuric acid, and then another one called perchloric acid, right, which has the perchlorate ion in it. So 6 strong acids. All of the other hundreds of acids, these just being a few of them, are weak acids. So all of our carboxylic acids, all of our carbonate and bicarbonate acids, and some of our binary acids are going to fall into this category of, and some of our oxyacids are going to fall into this category of weak acids. Now, how do we, look at maybe some other ways to think about how strong an acid is? So what makes something a strong acid versus and a base, or a weak acid versus base within the molecule? So if we think about acids, the strength of an acid really depends on how strongly the hydrogen is attracted to that, what would become the negative ion. So it's really looking at that hydrogen that is going to be lost. How strongly is it attracted to the rest of that acid molecule, right? How strongly is it bonded, right? And the stronger that attraction is, the weaker the acid is going to be, right? Because if we have a strong interaction, it's going to be hard to pull that hydrogen away, which is what's necessary for it to become an acid, right? For it to be lost. So if we have a very strong attraction, that's going to create a weak acid. If we have a relatively weak interaction, that's going to make the hydrogen easy to lose, and you're going to get a strong acid, right? Something that gives away all its hydrogen or loses all of its hydrogen. And so, while it seems sort of contrary, we want that hydrogen interaction to be weak within that acid if we're going to have a strong acid. Now, the way that we can look at this, again, is through the equilibrium. And looking at the value of the equilibrium constant K. Now, as we'll see, this is going to be called, in acid-base chemistry, we're going to call this an ionization constant, because an ionization is what's occurring, right? We're creating ions. And so, the smaller this ionization constant means the more reactant favored it is, right? So small k means it's reactant favored, and that's going to tell us that we have a weaker acid, right? An acid or base that has lost less or has been converted less into the ion form. The bigger the K, right? So if we have a large ionization constant, that's going to be indicative of a stronger acid. And again, the weaker this attraction is, right? The weaker this attraction is, more product forms. And stronger acid. So it really comes down to how strongly held that hydrogen is to the acid. Now, in terms of the base, right, again, it's going to look at, how strong the interaction is to wherever the proton donor is, right? So it has to have the ability to attract it, right? So it's going to really depend on the acid part to know, right, ability to extract that hydrogen. So the key is the equilibrium is how we'll look at these. So this is again the same idea, just in picture form. So weak attraction, complete ionization, strong acid. Strong attraction, only partial ionization, weak acid. So as I mentioned, the equilibrium constant here is going to be called an ionization constant. And if we're dealing with an acid, we call this an acid ionization constant, abbreviated as K, but we give it a sub A to specify it as an acid ionization constant. So it's just an equilibrium constant, right? It's products over reactants raised to their coefficients, but we give it a special notation to define it as an acid ionization constant. Now, the equilibrium that we're always looking at here is going to be our acid plus water goes to hydronium plus whatever the conjugate base would be, right, of our acid. So the A part, right, whether this is chloride ion or bromide ion or whatever ion it might be, right, whatever negative ion is the conjugate base of our acid. Now, you might also see it drawn like this, right? You can also see it with the water left out, where we just showed the dissociation where the acid becomes H plus and A minus, right? So a more simplistic form is to leave out the water on both sides. So we just leave it out on the reactant side, and we draw the hydronium as just H plus. So you'll see it both ways. And if I were to draw the equilibrium expression here, my products are going to be either hydronium times A minus or H plus and A minus divided by HA. Notice the water is not there, right? The water is a pure liquid, right? We leave those out of it, out of an equilibrium expression, because they won't affect the equilibrium. And so, again, ultimately it doesn't matter whether we put it in the reaction in terms of calculating the equilibrium, right? Leaving the water out doesn't change this expression, and so you're going to get the same equilibrium constant whether you draw it in this form or this form. So you'll see it both ways. Now, again, larger Ka means more product favored. More product favored means a stronger acid because you're producing more of the ion form, right? So the more you go toward products, the bigger K is going to be, which is indicating that you have a stronger acid. So larger Ka, stronger acid. Now, I definitely don't expect you to remember everything in this table, but what I want to do is just give you some ideas here. And first of all, these are all weak acids here. And so if we look at the Ka values, you can see they range, right? From things that are just, to the minus second to things that are to the minus 10th, right? So you have things like acetic acid that are to the minus 5th, hydrofluoric acid to the minus 4th. So you can see a lot of acids are going to be in this minus 4, minus 5 value for Ka, right? So pretty small, much less than 1, right? So these are definitely going to be reactant-favored reactions, right? Now, for things that are truly strong acids, we don't even have a Ka value because they're way over 1, right? And so it doesn't really even, make sense to have it in a table. Now, we're going to talk about this pKa value here a little bit later, but this is another way that we can define acid strength in terms of numeric. So, this is going to be a stronger weak acid, right? So all these are weak acids, but there's a scale, right? We have stronger weak acids and we have weaker weak acids. In terms of pKa, it's going to have a larger Ka and a smaller pKa, right? Those are things that are going to characterize your stronger weak acids. Okay, so that's kind of our initial look at how equilibrium is going to play a role in acid-base strength and how we're going to use it. Now, in the next section, in the next video, we're going to look at the pH scale, and in upcoming videos, we're going to look at the pH scale, and we're going to look at how we go about finding that pH for strong acids and weak acids. And so those are some of the things we're going to do in the upcoming videos.